this video, we're going to look at applications that can be solved by systems of equations. The first type of example we're going to look at is considered a mixture problem, in which you have several different goals that you're trying to hit. So the goals might be calories and various amounts of nutrients. It might be various amounts of money from different accounts that have different interest rates, or it might be various amounts of money and time that get spent in developing a product. Here we have somebody that needs 10 gallons of paint, and she's trying to mix two different colors. One color, called Dusty Miller, needs to be 30% of a certain white pigment, 60% of a certain blue pigment, and 10% of a certain yellow pigment. She also needs a second shade called Robin's Egg, and that needs 15% of the same white pigment, 75% of the same blue pigment, and 10% of the same yellow pigment. And she plans to use the paint that the shop already has. She has 3 paints. One already is 90% of the white pigment, 6% of the blue pigment, and 4% of the yellow pigment. The second paint that she has is 20% white, 80% blue, no yellow, and the third is 5% white, 40% blue, and 55% yellow. So we're going to set up a system of equations for each of these colors of paint and try to solve for how much of the 3 different kinds of paint she needs to blend to create Dusty Miller and to create Robin's Egg. To make 10 gallons of the Dusty Miller paint, 30% of the 10 gallons, or 3 gallons, needs to be white. 60% of the 10 gallons, or 6 gallons, needs to be blue. 10% of the 10 gallons, or 1 gallon, needs to be yellow. Let's identify our variables. Let X be the amount of the first type of paint that's going to be used in the blend, Y the amount of gallons of the second kind of paint, and Z the amount of gallons of the third kind of paint. So 0.9 times X will be the amount of white paint from paint 1, because remember, paint 1 is 90% of the white pigment. 0.2 times Y is the amount of white paint from paint 2, because paint 2 is 20% white. And 0.05 Z is the amount of white paint from paint 3. You want all 3 of those to add up to 3 gallons so that your Dusty Miller paint has 30% of the white. So our first equation is 0.9x plus 0.2y plus 0.05z set equal to 3. Similarly, for blue, the first paint was 6% blue, the second paint 80% blue, and the third paint 40% blue. We want there to be 6 gallons of blue paint in the blend of Dusty Miller, because we want 60% of 10 gallons to be blue. So our second equation is 0.06x plus 0.8y plus 0.4z equal to 6. And then for yellow, 4% of the first paint was yellow, none of the second paint was yellow, and 55% of the third paint was yellow. And we want 10% of the 10 gallons to be yellow, so 1 gallon out of 10 needs to be yellow. So the third equation is 0.04 times x plus 0 times y plus 0.55 times z set equal to 1. And below we have our full system of equations. This is a linear system of equations because all of the variables are raised to the first power. We can set this linear system up using matrices by making a 3 by 3 coefficient matrix. I have a 3 by 3 size matrix because we had 3 equations. They make the rows, and 3 variables, they make the columns. If I do dot products across the rows and down the column, I will read this as 0.9 times x plus 0.2 times y plus 0.05 times z equals 3. That was our first equation. 0.06 times x plus 0.8 times y plus 0.4 times z equals 6 is our second equation. 0.04 times x plus 0 times y plus 0.55 times z equals 1 was our third equation. If this coefficient matrix has an inverse, we can solve the system by using the inverse. If I multiply both sides of the equation by the inverse matrix, again, if the inverse matrix exists, then when I multiply the inverse of the coefficient by the coefficient matrix, it turns into the identity matrix, and the identity matrix times xyz will just equal xyz. Whatever I do on one side, I have to do the same thing on the other side. So the answer column matrix also needs to be multiplied by the inverse matrix. And doing that on a calculator, because the numbers here would be kind of messy in terms of finding the inverse, I get that xyz would equal 1.79, 6.52, 1.69. So again, the left-hand side ends up being equivalent to xyz because the inverse times the original coefficient matrix reduces to the identity matrix. The identity matrix times xyz will just be xyz. If I multiply the inverse of the coefficient by 361, I get a new column matrix which has my three answers. So it is possible to make the Dusty Miller shade. To get 10 gallons of Dusty Miller, she'll need to use 1.79 gallons of the first paint, 6.52 gallons of the second paint, and 1.69 gallons of the third paint. And if you've ever painted a room, you know that you really need the formula to be exact because it's really easy for shades of paint to look off. She also wants to make robin's egg, and she needs 10 gallons. So 15% or 1.5 gallons needs to be white, 75% or 7.5 gallons needs to be blue, and 10% or 1 gallon needs to be yellow. She's still using the same paints, and so X, Y, and Z will still represent the amounts of those three kinds of paint, and the coefficients are going to stay the same in my system as in the previous system because the first paint is still 90% white, the second paint is still 20% white, the third paint is still 5% white, but this time I need 1.5 gallons total of white. 6% of the first paint is blue, 80% of the second paint is blue, and 40% of the third paint is blue, and I need 7.5 gallons of blue. 4% of the third paint is yellow, or sorry, of the first paint is yellow, none of the second paint is yellow, and 55% of the third paint is yellow, and we need 1 gallon of yellow. So my system is actually going to start off with looking the same. It has the same coefficients, but my answer column will be different than to make Dusty Miller. The answer column this time will be 1.5, 7.5, and 1. We discovered when we solved the previous system that this coefficient matrix does have an inverse, and we were able to get the solution. So we could use that method, but just to point out a different method, why don't this time we form the augmented matrix and use row reduction to find our solution. So, but what we mean by an augmented matrix is you put all of the coefficients and the answer column into a new 3x4 matrix. And then we go through the process using the elementary row operations to try to turn the coefficient matrix into the identity matrix. And we will be able to do that with enough patience or with a program if the coefficient matrix does have an inverse. So we already know it has an inverse, hence when we do the row reduction, we should end up with the coefficient matrix turning into the identity matrix. I used Desmos to run the RREF program. Again, RREF stands for, row reduction, row reduced echelon form. And we get 1 times x equals negative 0.319693. 1 times y equals 8.47826. 1 times z equals 1.84143. So we have a solution. I mean, the system mathematically has a solution, but in terms of this application, I can't put a negative amount of the first paint into my blend. I could put 8.47 gallons in, I could put 1.84 gallons in, but there's no way for me to put a negative amount of paint in. So there is actually no way to form the shade robin's egg with those 3 shades of paint. Mixture problems can be about a lot of different topics. In this case, our coefficients were rates of amounts of paint in different blends, and our totals were total amounts of shades of paint in gallons. And it was important to carefully read across the equations to make sure that I'm putting all the coefficients for white paint in the same equation to get a total amount of white paint, and all the coefficients for blue paint to get a total amount of blue paint, etc. If the word problem was a nutrition problem, you would want to put the rates of calories in the same row so that you were getting the total amount of calories, and the amount of potassium or whatever other nutrients you were interested in, all in the same row to make sure you're getting the total amount of that nutrient. Or you might have a problem about hours that it would take to complete a job, and so the coefficients would be how many hours per task, and then that would need to add to the total amount of time. So before you get busy actually solving the system, take the time to reread your equations and make certain that you have the appropriate coefficients in the appropriate rows. Balancing a system of equations is like a mixture problem. You are blending molecules so that the amount of atoms are even. And here we have 4 molecules. X, Y, Z, and W will be the amounts of each of those molecules as we build the chemical equation. We'll have 3 equations because there are 3 elements building these molecules. So each element will have its own equation. An equation for carbon, an equation for hydrogen, an equation for oxygen. The first equation for carbon will be 4x plus 0y equals z plus 0w. There are 4 carbon atoms in the first molecule. So 4 times x is the total amount of carbon, and 0 times y is the total amount of carbon from the O2. 1 times z is the total amount of carbon from the CO2, and 0 times w is the total amount of carbon from the H2O. The second equation is for hydrogen, and it should be 10x plus 0y equals 0z plus 2w. There's 10 hydrogen in the first molecule, no hydrogen in the second, no hydrogen in the third, and 2 hydrogen atoms in the fourth molecule. The third equation will be for oxygen, 0x plus 2y equals 2z plus 1w. There's no oxygen in the first molecule, 2 oxygen in the second, 2 oxygen in the third, and 1 oxygen in the fourth. We will get a solution for this system, but it will not be a single point solution. If you get a single point solution, you had to have had as many equations as you have variables. Now, having the same number of equations as variables doesn't necessarily mean you're going to get a single point solution, but there's no way to get a single point solution if you don't have the same number of equations as you have variables. So here we'll get a linear combination for our solution. Now for the next step of solving our system and using matrices, we will need all of the variables on one side of the equal sign and constants on the other side of the equal sign. So the 3 equations that we had will be rewritten as 4x plus 0y minus 1z minus 0w equals 0. And then the second equation, 10x plus 0y minus 0z minus 2w equals 0. And then 0x plus 2y minus 2z minus w equals 0. You don't really have to write the 0y and 0w, etc. I'm putting them in there so that we don't lose track of what coefficients should go where. So I find it helpful to have those variables still in as place values, even though their coefficients are zeros. We already mentioned how we are not going to get a single point solution. Therefore, there's no point in me trying to find the inverse of the coefficient matrix because it is not square. So I am going to make an augmented matrix. Again, an augmented matrix means you have columns for the coefficients, and then the last column is your answer column. And then we're going to do RREF, the row reduced echelon form, and I will let Desmos or my graphing calculator run this for me. And I also use the fraction mode so that the final results are listed in fraction form. And we end up with the following row reduced form. So that first row reads as 1 times x minus 1/5 w equals 0. And then y minus 13/10 w equals 0. And then z minus 4/5 w equals 0. And so I can build my solution off of those three short equations. If you want to, you could rewrite the equations so that you're reading it as x is equal to 1/5 w, y equals 13/10 w, and z equals 4/5 w. And any whole numbers that would work to make all three of those true can be used as your amounts of the molecules. It makes sense to pick the smallest, simplest numbers that you can. And in this case, if w was 10, that would give us whole numbers that are the smallest. So if w is 10, x would be 2, y would be 13, and z would be 8. So my equation balances as 2 butane plus 13 O2, and on the other side of the chemical equation would be 8 CO2 plus 10 H2O. And notice if you take 2 times 4, you get 8 on the left side, and then over on the right side, I have 8 times 1 carbon, so the amount of carbon on the left equals the amount of carbon on the right. 2 times 10 is 20, and on the right-hand side, 10 times 2 for the H2O is 20, so there's the same number of hydrogen on both sides. And then 13 times 2 is 26 on the left for oxygen, and 8 times 2 is 16, but then 10 times 1 is 10, and 16 plus 10 is also 26. So if you go across and look on the left and look on the right, there's a total amount of carbon on the left matching a total amount of carbon on the right. There's a total amount of hydrogen on the left matching the total amount of hydrogen on the right. And same thing for the oxygen. So we have correctly balanced our equation. Again, people can balance chemical equations often just by looking at them. The simpler they are, the easier it is to do that. The point here was to illustrate how they can be balanced by using systems of equation and treating it somewhat like a mixture problem. Another type of application for which systems of equations can be used are about different economies that share resources or transfer resources back and forth. Your book has examples with transportation and utilities and raw materials. You can look at those examples as you're practicing. Here we have a made-up economy of a company that makes different snacks. And so cheese popcorn sector provides 20% of its resources to chocolate covered peanuts, 30% of its resources to graham crackers, and 25% of its resources to barbecue potato chips. And the rest of the resources for cheese popcorn remains with cheese popcorn. Chocolate covered peanuts, on the other hand, provides 40% of its resources to cheese popcorn, 15% to graham crackers, 35% to barbecue potato chips, and the rest remains with the chocolate-covered peanut economy. Graham crackers provide 65% to cheese popcorn, 20% to barbecue potato chips, and keeps the rest. So notice none of the graham cracker resources goes to chocolate-covered peanut resources. Barbecue potato chips provides 20% of its resources to the other three, and the 40% remains in its economy. So we're going to set up a system of equations to solve for the allocation of resources, and we'll solve the system and clearly state our solution set. The rows or equations are for each of the different sectors, and so one row or equation will be for cheese popcorn, one row or equation will be for chocolate-covered peanuts, one row will be for graham crackers, and one row or equation will be for barbecue potato chips. I'm letting C stand for cheese popcorn, P for chocolate-covered peanuts, G for graham cracker, and B for barbecue potato chips. The columns will be the coefficients that build the different percentages for the different sectors. So the first row needs to equal one full sector for cheese popcorn. The second row needs to add to one full sector for chocolate-covered peanuts. The third row needs to add to one full sector of economy for graham cracker, and the fourth row needs to equal one full economy sector for barbecue potato chips. So then to build cheese popcorn, 25% of cheese popcorn remained in cheese popcorn, and then 20% and 30% and 25% got added to the other sectors. So in the cheese popcorn row is the 25% times C that remained with cheese popcorn. Then chocolate-covered peanuts gave 40% of its economy to cheese popcorn. So I'm adding 0.4 times P to the 0.25 times C as I build the economy for one full cheese popcorn sector. Then 65% of graham cracker was added to cheese popcorn, and 20% of barbecue potato chips was given to cheese popcorn. So those are all of the amounts that add up to the full sector for cheese popcorn. And then similarly, you could go through the percentages that builds the chocolate-covered peanut sector and builds the graham cracker sector and builds the barbecue potato chip sector. So kind of look carefully at my system here, that each row is an equation that builds the one full economy. The columns are the percentages of each sector that went into the different sectors. Now, when we solve a system of equations, we want all the variables on one side and constants on the other side. So on the right-hand side of the initial equation, I have 1 times C, 1 times P, 1 times G, 1 times B. So I need to move those variables to the other side. So 0.25 minus 1 gives me negative 0.75 C. And then notice on the right-hand side, it's now equal to 0. And 0.1 times P minus 1 times P is negative 0.9 P. So in the second equation, the chocolate-covered peanut column now has negative 0.9, and notice on the right-hand side it now is 0. So we do that for all four equations, move the variables over so we have variables on one side and constants on the other, and then we are ready to set up our augmented matrix. Okay, so I am going to use an augmented matrix. Notice the coefficients are the columns and the answer is the last column. They were all zeros. I am using Desmos to find the row reduced echelon version of that augmented matrix, and the fully reduced row echelon matrix is on the right, and I read that as 1 times C minus 1.15044B equals 0. The second row is P minus 0.477876B equals 0. And then 1G minus 0.725664B equals 0. So all three of the variables, cheese popcorn, chocolate-covered peanuts, graham crackers, are written in terms of barbecue potato chips. So if the barbecue potato chip economy was $4 million, then the cheese popcorn economy would be $4,600,000, because that is 1.15 times 4 million. The chocolate covered peanut economy would be 1,920,000 because 0.48 times 4 million is 1,920,000. And the graham cracker economy would be 2,920,000 because 0.73 times 4 million is 2,920,000. So in this economy, the way we set up the system, 3 of the variables got written in terms of the fourth. And so then if you knew, an amount for the fourth, you could find the amounts of the others. This next example is called a migration pattern. And we're going to look at a 2x2 example. You could actually have more variables, but it gets more complicated the more variables you have. So we're going to stick right now with just a 2x2. And it's a situation in which amounts move back and forth between 2 different populations. So you might have people moving from suburbs into a city and from city into the suburbs and vice versa. You might have people switching back and forth between 2 different products, such as, 2 different, Wi-Fi or phone companies. Here we have 2 different budgets. We have a marketing budget and a general fund. And each year, 8% of the marketing budget gets transferred into the general fund due to, certain projects. And 16% of the general fund gets transferred into the marketing budget. So we're going to set up a difference equation that explains the migration pattern. And if we start off with 2.8 million in the general fund and 6.2 million in the marketing budget, we're going to find how much will be in each fund 8 years from now. We'll let X be the amount of the marketing budget and Y be the amount of the general fund. Okay, remember X was marketing, Y is general fund. If 8% of marketing goes to general fund, that leaves 92% staying in marketing. And then 16% of general fund went to marketing. So 92%, 0.92 times X plus 16%, 0.16 times Y equals the new amount of marketing. 8% of marketing went to general fund. 84% of the general fund stays in the general fund because 16% went to marketing. So turning that system into a matrix equation, we have the coefficient matrix 0.92, 0.16, 0.08, 0.84. Notice, dot across the row and down the column, and, you'll notice that you're building the correct equation that we had above. Then think about if you use that and you get a new amount of marketing and a new amount of general budget, and then you put those new amounts into the original equation. The new amounts were created by taking that coefficient matrix and multiplying it by the original amounts. So putting the new amounts in is equivalent to squaring that coefficient matrix and multiplying that by the original amounts. If you then took the second year amounts and plugged them back in, it would be equivalent to cubing that original coefficient matrix and multiplying by the original amounts. So if we want to know 8 years from now, let's take that coefficient matrix and raise it to the 8th power and then run that 8th power of the original matrix through the original amounts. So taking my coefficient matrix, raising it to the 8th power, multiplying by the column vector 6.2, 2.8, it gives me new amounts of 6.02 million for the marketing budget and 2.98 million for the general fund budget 8 years from now. Systems of equations can also be used to fit models or formulas to data. Here we're going to do an example in which we have 3 points and we're trying to fit a quadratic polynomial to the 3 data points. We have x coordinates 4, 1, and -5, and they correspond to y coordinates 43.8, 17.1, and -9.3. Notice when I put the x values into the quadratic equation and I put the y values also into the quadratic equation, I form 3 linear functions. Again, we're trying to fit a quadratic model, but if you put the values in for x, The variables end up being the coefficients that I'm looking for. What coefficient should multiply x squared? What coefficient should multiply x? What should be the constant? So we create a system of linear equations when we plug x and y into this quadratic formula, and we can solve this system like we have our other systems. My system of equations can be put into the following matrix equation. Notice if I read across the first row and I dot it with the column vector ABC, I will get 16 times A plus 4 times B plus 1 times C, and that will equal 43.8. That is the first set of data plugged into the quadratic equation. And then 1 times A plus 1 times B plus 1 times C equals 17.1 is the second set of data plugged into the quadratic equation. And then 25 times A minus 5 times B plus 1 times C equals negative 9.3 is our third set of data plugged into the quadratic equation. For this system, we will use the inverse matrix method, and so if we multiply the left side of our matrix equation and the right side of our matrix equation by the inverse of the original coefficient matrix, we will end up with ABC equaling a column vector, and the column vector will contain the coefficients of our quadratic equation. Using that method, we end up with the coefficients of our quadratic equation. Notice when I graph on Desmos, the coefficient 1/2 times x squared plus the coefficient 32/5 times x plus the constant 51/5, I get a parabola that goes right through my 3 points. So this method can be used for other types of equations. With a quadratic, though, you get a nice 3x3 system. For other size polynomials, you'll have different size coefficients. For other types of functions involving maybe trig functions and so forth, you'll have messier coefficients. But anyway, it's a method that can be used if you have a set of data to fit different types of formulas to your data. So we've seen a variety of different applications here. Each application kind of fits into a form in which you'll recognize that there are other applications that fit those forms. We saw mixture problems, we saw migration patterns, we saw sectors of an economy sharing resources, and then here we were fitting data to equations. As you look through the book and you look at applications in the real world, you'll see that many fit these different forms.